Hello and welcome back to World Turtles. I'm currently working very hard trying to cram as much polished content as I can into the game in time for the June Steam Games Festival, or Next Fest as they're calling it now. I'll be setting up live streams for the event and would appreciate if some of you can have a test run with me, as I've never done it before, so please keep an eye out for more detail early June. Now, sometimes progress feels a bit slow, and other times I'm ecstatic after implementing something major in a day or two. Today I can show off a few of the additions I've made over the last 2 weeks, and I think they really bring the map to life. So enjoy the ride! Let's start off with shaders. My knowledge of shaders is a bit shady, although I am now learning rapidly. What I do know is they are an extremely powerful and performant tool for making it look like something is happening without expending the system resources to actually make it happen. What do I mean by this? Let's look at an example. When the woodcutter chops a tree, the little shiver the tree makes is actual, in that the model itself is rotated in 3D space, a little bit to one side and then back again, over a short period of time. This looks very nice and is no problem when a few trees shiver at a time. You can also try to use this technique to let trees gently sway to and fro to simulate wind. However, add more than a few trees and this starts getting expensive, and your frame rate drops. But using shader tricks you can keep the models completely still and rather slightly manipulate the way the triangles are drawn. For example, the movement in these flowers are all shader based. I applied the same shader to the trees. We are limited in how much movement we can get before it starts looking as if the entire tree is moving around, but we only need the slightest of changes to make it look realistic enough and add great value to the overall look of the scene. Now, something that is quite easy to implement a basic version of in shaders are normal maps. These can drastically improve the look of a two-dimensional texture by specifying different normal vectors for different parts of the texture. The normal vector at a point on a surface is basically in the direction you'd take if you wanted to get as far away from the surface at that point as possible. In other words, a vector perpendicular to the surface, outwards. This is also the direction from which light needs to hit the surface if you want to illuminate the surface as much as possible. The more the direction from which the light hits that point on the surface differs from the normal, the darker that plane is going to look. We can apply this knowledge to our two-dimensional textures to make them seem more three-dimensional. In reality, the normal vector of our flat texture is always in the same direction. In this example, we're looking straight at a rectangular plane, with the normal vectors pointing towards us, and light shining from us onto the rectangle. If the sun shone onto the rectangle from somewhere to our right, the entire rectangle would darken a bit, since the normal vectors are all equal and the rectangle reflects less light back to our eyes. But we can override these normal vectors with virtual ones. Let's divide our rectangle into 4 thinner ones. Then color the second one from the right a bit lighter and the one to its left a bit darker. This changes our perception of the flat texture. It now looks like a ramp has appeared, and if the light was shining from the left, it would look like a dip. The same basic idea is applied in shaders using normal maps. The tents of the Founders Hex and Wanderers cabins have always had normal maps implemented. Consider the little folds and wrinkles in the cloth. While the texture itself does hint at these, it's in the normal map that it really transforms into something that looks three-dimensional. You may ask why we couldn't just make the texture more detailed. Surely it would give the same effect. And you actually could, but you would have to redo it for every different direction the light could come from. Let's see why. The version of our rectangular bars created by changing the color on some parts of the 2D texture is exactly the same as one that would result from setting up a normal map with one appropriate normal vector for each of the 4 bars, but only with the light coming from exactly the direction we had before. If the source of the light now moves a little bit, the intensity of the color on each bar needs to change as well. We can calculate this change using the normal vector and the new direction from which the light shines. However, in the case where we only changed the colors of the two bars, we still have the same normal vector for the entire texture. So our adjustment calculation is going to lead to the same adjustment for the entire texture. The entire texture becomes lighter or darker homogeneously. We don't like that, since it ignores the virtual bumps and 3D information we try to work into the 2D texture. It assumes that the change in light angle impacts the intensity of all virtual bumps exactly the same. But a plane that's already turned away from the light is already very dark, and would only be affected a small amount by turning even further away. In fact, the surface that's being hit perpendicularly by the light is the most affected. While the more the normal vector changes from this direction, the less the impact becomes, since the relative change in light received diminishes. If we could just find a way not to have to manually redo the optimal color changes each time the light source changed position, that would be grand. And to do that, the normal vector is exactly what you need. We're basically arming our shader to recalculate the intensity for any direction from which the light hits each point on the surface. We can see this in action beautifully on our roof texture. Without the normal map, the one side of the roof consists of 3 quads or rectangles. While the texture does contain a decent amount of differentiation, as we rotate around, we can see how the intensity of each quad changes, with no differentiation on each separate quad. The intensity gets calculated once off for each quad, and while we can't see the edges between quads when viewed from the front, we clearly see the edges between quads the more we see it from the side. Now, when we add normal vectors, the intensity can be better calculated for points on each quad. Each point gets a tailor-made intensity adjustment, and the clear edges disappear, leaving us with a better viewing experience from different angles. But how do we get the normal vectors? Isn't that a lot of work? Isn't it equivalent to making the model itself a lot more detailed so that we actually have more and more real normal vectors for triangles and less flat texture? Again, shaders can help us cheat a bit to almost make it look like the real thing, within reason. Remember how a decent texture can almost do the same thing that normal vectors can, but only from one angle? Well, let's use that. We have the solution for one case, so if we could determine which normal vectors would mimic this solution, we have a decent set of normal vectors. And applying those normal vectors works quite well. There are many software packages that can create normal maps from textures, and playing around with their parameters gives you a lot of options to tweak your end results. I used Photoshop to create normal maps for our main buildings, and it immediately made them look less flat and made the world more immersive. While we're looking at the buildings, note that I've also implemented proper upgrade levels for them. You start off with something plain and small, but can upgrade both the cabin and the outbuildings. The same progressive construction methodology is used to break down part of the model should it be required, and then apply the improvements. In the game, you'd have to pay for these upgrades, and the units would first have to gain enough experience over time. But since I have access to the source code, I can upgrade as I wish. I've added another improvement to the buildings. The color of the tent material and roofs can now be set to any color you like. This is achieved using another shader trick called color masking. In addition to passing the base texture and the normal map to the shader, we pass another texture to it. This contains a color map of the base texture. In our case, the entire texture is roof, so our mask is completely red. The shader caters for 3 color masks in the red, green and blue channels, but we're only using the red here. Note that our base texture is grayscale, although our roofs are colored by the color selected for the red mask. This tells the shader to tint anything on the base texture that coincides with the red mask by the selected color. The entirety of our grayscale texture therefore gets the colored tint and is rendered in that color. This does limit the colors we can use on this part of the building, but you can do a lot with different intensities of the same color. And it allows us to merely change the color associated with the red mask on the material to update all models that use this material to this new color in a flash. By duplicating this material and setting different roof colors, we can now combine different player or team colors to help visually differentiate different realms. This is also helpful for things like flag and unit colors. The last thing I want to mention regarding the buildings before we get to the grand finale is the emissive windows, yet another shader trick. Certain image formats, specifically .tga, allow you to store an alpha channel in addition to the normal RGB channel. This acts a lot like a color map we discussed just now. On this channel, we indicate everything on the texture which we want to emit light. Then tell the shader to apply a certain emission color to these parts. This gives us the striking window glow effect, which adds so much joy during darker times. And now for the final item on our list, using normal maps on the terrain shader for some subtle and some dramatic effects. While we don't want our terrain to be too detailed, since the foreground would then get lost in it, we also want it to contain enough subtle variation to prevent it from being visually patterned. I therefore experimented with tagging a normal map onto our terrain shader, something with soft blowing bumps and dents to just alter the terrain a little bit. By tweaking the weight of the normal, we can find something that isn't too powerful while still leaving a few interesting bumps and dents here and there, as opposed to the terrain texture on its own. After basking in my own glow for a minute or two for managing to add something this simple to a shader, I immediately thought of a more dramatic possible application for this. But I didn't want to lose the bit I just completed, so I thought I'd try adding a second normal map for this exercise and average the weighted normal vectors to get the final normal vector, which worked. I wanted to see whether I could simulate the shadows of unseen clouds on the terrain. So our normal map is just an undulating random noise texture, where the lighter parts represent cloud shadows. And increasing the weight includes larger parts around those focus points in the shadow. We sample this texture at the world coordinates of the pixel to be drawn and set the terrain's normal vector at that spot. Now, if we cycle through the texture over time, it means the normal vectors would shift around on the map as we play, and the simulated shadows would make its way over the land as if the turtle is flying past underneath some clouds or other objects in space. By lerping the weight up and down, we can let the shadows grow and shrink, and linking this to an increasing and decreasing directional light intensity, we can sort of mask the fact that the shadows don't actually affect anything placed on the terrain, by also darkening the entire scene. If you let your brain roam free, it would convince you those are proper shadows. On the other hand, it's probably nice to still be able to see your buildings, units and resources in a severe storm, especially if you have to keep playing through it. We can also randomize the weights so different storms have different intensities, and we can keep faint shadows crossing over the terrain for a dynamic look, or remove them on a crisp, clear day. All these improvements combined makes this a fairly major upgrade, although not much has changed in the gameplay mechanics itself, except for upgrading the buildings. After updating all the building types with upgrade models, I'll continue implementing the complete upgrade mechanic. I've also already spent a lot of time on an overview screen, which would make the aim and flow of the game a lot clearer, and would be where you manage your realm-wide research, choices and progression. Please subscribe if you'd like to stay up to date with my progress on the game. Goodbye!